the power module was always envisaged to be didn't need to be maintained on the train, so it was all packaged into this this underframe box, if you like, called a raft, with the idea being that you would never have to maintain it on the train. You just take it off with a forklift and sort it out offline. And it went through 2 or 3 iterations, the diesel genset concept, until it got to what we know today on the Transport for Wales fleets. I'll come to that. But you can see there the real benefit of being able to take them on and off with a forklift, and that came into its own when we introduced the first diesel versions into passenger service. I think there was one occasion where a train came into Bletchley and had an engine swap between diagrams in about 45-minute turnaround. So that's that. Remember that picture, because the batteries essentially fill the same space. Another thing you had to do in creating this Class 230 was to create a more robust, crash-worthy structure on the front end to protect the driver. Obviously, the trains in their original form had really no crashworthiness to speak of, because the underground is a closed system where it's not expected to come into contact with anything other than perhaps other trains. So there's no level crossings, no foot crossings, nothing really to threaten the train. Obviously, when you take them out of the underground and put them on the national network, there's a risk that they might come into contact with things on level crossings. So a big piece of work was done with the Rail Accident Investigation Branch to look at what was most likely to come into contact with one of these trains on the routes that it was intended to run on. And a crash structure was designed, which is the image on the left, basically a crash cage, really. And that was designed to give us survival space in the event of an impact. So it was all designed in CAD, and obviously analysed through FEA and all that stuff. But to actually validate the model and the survivability of the structure, a real-life test was done where a train was crashed into a tank of water, 3-ton tank of water, at 40 miles an hour. And you can find that video on the internet. It's quite exciting, not as exciting as the nuclear flask test back in the 1980s. But the correlation between the real life results and the actual design was very, very close. So a victory for the FEA results there. Okay, this is a bit of a whirlwind tour of the Class 230 before I get onto the fast charge, but this was the first train. And again, this was actually 230001. The original, in its original incarnation, was a 3-car diesel electric multiple unit. And it was approved for running on the main line, originally from Longmarston in Warwickshire down to Honeybourne and on that line. But yeah, as you can see there, to the passengers, we put a PRM toilet in the middle car. Lots of additions that made it look and feel like a new train. That was always the intention, underground train, although it did unfortunately get that sort of got that reputation, probably a bit unfairly. The second train we built was a 2-car battery train, incorporating most of the features of the original diesel electric version, but instead of those genset rafts underneath, as you can see the inset picture there, you have battery rafts. I think these were the batteries that came out of the independently powered EMU project, which was something that Network Rail and Bombardier did back in 2013 to hybridize a Class 379 Electrostar. And when that project ended, I think Vivarail inherited the batteries. So they were packaged into that form factor, that familiar raft. And 23002, as it became, 2-car battery unit, was taken up to the Bowness and Kinneil Railway and demonstrated to the public. Never actually ran on the main line in that form, but that's just the start of it. Then we got into several other iterations of Class 230, illustrated by this picture here. So we had the DEMU prototype, the yellow and green one, 23001. That essentially spawned three 2-car diesel electric multiple units for West Midlands trains, which until Vivarail went bust were running on the Bedford Bletchley line. Then that spawned a hybrid version. Well, if you like, you added together the diesel and the battery version and created a diesel battery hybrid. 3-car or 5x3-car trains for Transport for Wales, which are now operating on the Borderlands route between Wrexham and Bidston. Then there was a bit of a cul-de-sac into Vivarail Electric for the Isle of Wight. Those trains might have been battery at one point, but at the last minute, a decision was made to keep the electrification on the island, probably quite rightly. So we had to sort of swerve and change it into a third rail electric version, which isn't the same as the third and fourth rail electric version. It's very different. And those are now successfully operating and have been for 2 or 3 years on the island. Incidentally, they had to be the car bodies had to be lowered slightly for the Isle of Wight to ensure they'd fit through. It wasn't actually Ryde Tunnel. Right, everyone thinks it's Ryde Tunnel, but it's a bridge just to the south of Ryde Tunnel. So as you can see there, it's still quite a tight fit, but still certainly more generous than the previous trains that they replaced. And just to round it off, we built 2 battery trains that went to America, and then we converted 23001 back into what we might call the second generation battery train with different types of battery on it from the original 23002, and we took that to the COP26 conference in Glasgow in 2021. And we ran it in and out of Glasgow Central for 2 weeks, carrying invited guests, ran it down to Barhead, which is on the way to Kilmarnock, and we also ran it across the Forth Bridge. So it became the first pure electric train, if you like, to cross the Forth Bridge. And then finally, the same train, 001, in its battery incarnation, has become the train that is now owned by Great Western, which is what we're here to talk about. So it's been an absolute whirlwind of a few years, working all these variants. This is 001 whilst it was resting at Long Marston, in between its battery life and its so in between being a genset powered train and a battery train. As you can see, it got into quite a state, stood there for about 3 years, until finally the decision was taken in, I think it was probably January 2021, to have it ready for the climate change conference in November. So we had from January to November 2021 to basically restore that train and convert it to a battery unit from that state you see there. So the way we did that, in very simple terms, that diagram I showed earlier, we didn't need all the diesel related bits and pieces, didn't need the engine or the generator or the inverter or any of that stuff. We replaced that really with some big batteries which give a DC input to the TCU, which is supplied by a company called Structon. And of course, batteries not only power the train, but they also provide an energy sink for regenerative braking. Mechanically, we had to do a lot of changes to the underframe to fit them all in. Now the big blue lumps there, those are the batteries supplied by a company called Hoppecker in Germany, and they each weigh about 1.7 tons. And they've got a nominal 84 kilowatt hours of energy in them, and as you can see, we could just about squeeze 3 of them in between the bank of 2 and the one on its own are some DC-DC converters. Those are, each of the batteries has its own little heating and cooling unit to maintain a steady temperature essentially of the battery. What you don't want the battery is it always getting hot or too hot or too cold. So each battery raft has its own onboard thermal management system, but to power that you need a DC-DC converter, which takes the high voltage of the battery, which is about 600 or so volts, and steps it down for the voltage needed by the HVAC units. And to accommodate those batteries, you have to shift a lot of other things around, which I won't go into, but you can see the magnitude of there's not much space under those cars, and there's also a lot of weight to add as well, so we have to be very careful about where we place the weight and how we attached it. At the same time, we're doing some other changes to make the whole interior design a little bit more rational. Up until that point, a lot of electrical control boxes had been under various seats all spread around, so we decided to marshal them into 2 nice, well-organized cupboards at the body ends, just like normal trains. And that made the wiring a lot simpler, and also allowed for future changes, really, because every time you made a change, it would involve a lot of messing about. So we essentially packaged it all into these end cupboards to make life easier for ourselves. Originally, the D-Stock didn't have this walk-through gangway, So that was something we developed for TFW, and we rolled over into this COP26 train. And you can just see that picture there. We also, as if that wasn't enough, we had a rethink on the cab crash structure, which I showed you earlier. The original crash structure had to be welded in place or in situ. So it was, if you got the first weld wrong, the rest of it was a nightmare to sort out. So what we've now got is something that can be welded in, can be jig welded offline and then bolted together in the cab. So obviously you can control the tolerances a lot better when you build it offline. The challenge given to us at the time was that the cab should only take about 300 hours to build. Prior to that, each cab took about as long to build as the rest of the train combined, because it was such a confined space. I think we massively overachieved. It we actually built the cab in far less than 300 hours. I forget what the figure was now, but because of this modular concept, it was much easier to put together. Here's just a diagram to show that it isn't just about the big lumps of equipment when you're designing a train. It's also where on earth do you put all the cables, some of which are quite sizable. We always start the design with this sort of diagrammatic form, where you sketch out where you want your cable runs to be, and you obviously try and separate high current carrying from control voltage signals, otherwise you get EMC problems. And you take that and you turn it into a mechanical design. Now, with there being 3 batteries and each of those batteries needing big cables going to and from it, we actually ran out of space to carry them in the normal channels. So we had to design a special floor, if you like, to carry the cables over the top of the batteries. The floor also formed a sort of fire barrier, well, not sort of formed a fire barrier as well as carrying the cables. So it's sort of 2 jobs in one. So that was a lot of redesign, and this was the end result. Very smart looking train. These pictures were taken at the COP26 conference, and it was, well received. We were running in and out of Glasgow, next to the Hydroflex, the Porterbrook Hydroflex, and that's essentially how the train has remained. And there it is over Forth Bridge. So on to fast charge. Well, I've talked about the battery train. The elephant in the room, obviously, with battery trains is that they only have a finite range, and that's obviously a lot less than your average diesel train, which can go for 1,000 miles between refueling. So you have to conceive of a way of charging a train. When Adrian was still with us, and he was driving this concept, he said, the criteria was that you didn't want the driver to have to get out and plug in a cable. You didn't want to have to sit around for half an hour while the train charged. You didn't want to have to swap any batteries around. None of that was practical from an operational rail perspective. So you have to find another way of doing it. What we ended up with is essentially an automatic charging system, where the batteries, you'd have to change the batteries on the train. Well, I'll step you through now how this works. This is a graphic that people might be familiar with. So you have the onboard batteries on the train. These are the main constituents of the system. Because of the energy we're talking about, you can't if you want to charge this in a short space of time, we're talking 5 or 10 minutes at the average sort of terminus turnaround time. You're talking quite high currents and high power, and if you're trying to draw that sort of current out of the national grid, it's generally going to be very expensive, if not practically impossible. So you need some sort of energy buffer in between. So as well as the batteries on the trains, you've also got a trackside battery bank, which is your energy store, and you charge that up. You sort of trickle charge that when there's no train around, which gives you enough energy to give the train a real thump when it turns up at the high levels of current that you need. Stepping through this, then the train arrives. The train is in control all the time of how much energy it requires, and the onboard software controls that whilst talking to the trackside battery bank. The interface between the train and the trackside energy storage are some charging rails. These are positioned in the forefoot. They look quite like normal third rail, but they are normally earthed when there's no train around. One of the stipulations, the sort of famous stipulations at the moment, is that you can't have any more third rail electrification. Too dangerous. So to have this system, we had to convince ORR that the charging rails would only be live when a train was on top of them. In other words, the train was protecting the rails from coming into contact with any people. So the charge rails are in the forefoot, and those are connected to the trackside battery bank. There's a communication system between the train and the battery bank to ensure that it's the right train in the right place. It's safe to receive. It's positioned correctly, and the connecting shoes are down. I'll come to the connection shoes in a minute, but there's about 3 or 4 different levels of handshake that go on between the train and the trackside battery bank. So train pulls up, parks over the rails, a special set of shoe gear come down, connects with the rails, and then everything happens automatically. All the driver needs to do is stop the train in the right place, and we're not talking a stopping distance or stopping tolerance any more accurate than the average stopping tolerance, if you like, at a platform. The charge rails are long enough to accommodate a bit of leeway. And all the driver sees is a light in the cab that says that it's charging. As soon as the brakes come on, essentially the charging commences. And as soon as the driver puts the train or takes the brakes off and puts the train into the first notch, the charging automatically ceases and packs up, and off the train goes. So there's a slight lag between the driver going into first notch or whatever, but essentially the driver doesn't have to do anything. And then once the train is gone, the trackside battery bank recharges using a fairly low power connection to the grid. I think we're talking the one at West Eden is going to be a 63 amp connection, 415 3-phase connection. Getting back to the batteries on the train, these are the Hoppeker batteries in a bit more of a close up. They are force cooled, if you like, so they have active cooling because of the heat generated when charging at high charge rates. Obviously, you need to thermally manage them. So that's why they have got all those cooling pipes and radiators and stuff. That's all to do with the thermal management of the batteries. As you can see, every available inch has been filled under the train. They're really up against the gauge line. If we were doing it again, we'd probably design the batteries in a different orientation. The only reason they're like that is because they were mimicking the original diesel genset form. But that doesn't mean they have to be like that. There's probably a better way of doing it now if we did any more to have a much more gauge friendly battery and weight friendly as well, mass distribution friendly. Then there's the special shoes, the special shoe gear, as we call it. Now what you see on the left there, that's 3 short lengths of charge rail in the forefoot. Now my graphic I showed earlier, there was only 2 rails, but in fact in real life there's 3. You have a middle rail that's positive, and the 2 either side of it are negative, and that's to allow for the train to come in any direction. The shoe gear on the train is actually offset from the center line. That's so that the positive shoe on the train is always going to match up with the positive rail, so there can be no risk of the incorrect polarity, which should obviously be bad. The length of the charge rail shown there, they were only there for test purposes, as also are the big sheets of perspex. So those are there because where we were previously testing at Bletchley Depot, there was concrete in the forefoot. Obviously, there wouldn't normally be concrete in the forefoot like that. It's just because that's the old CET emptying road. So we put those sheets down to protect the shoe from the concrete. The shoes are normally retracted using a pneumatic cylinder. So when the train's moving, those are retracted and they're well within gauge. When only when the train is coming into the charging station, those shoes deploy just before you get to the rails, and then they run up the rails in order to clear the rails of any debris. That's obviously quite important because if you haven't got proper mechanical contact between the shoe and the rail, there's a risk of hot spots when you're putting the high current through it. So those shoes go up and down, and when we were Vivarail, we had a test rig out the back of the yard. We called our endurance test rig, and I've got a video I'll show perhaps at the end. But in order to test this shoe gear, not to destruction, but to test it through 20,000 cycles, which represents a year's worth of operation. I think we actually did it for more than that. I think we did it for 2 years worth of operation. We had the shoes going up and down the rails, backwards and forwards. The Heath Robinson contraption you can see there was built from two P-way trolleys with various boxes bolted to them, but that did the job. So this thing shuttled backwards and forwards for quite a lot of last year in all weathers, because the problem is, having never done this before, there's no way of validating. You can do it with the FEA, but there's no way of actually validating it. So we had to build this rig in order to prove to ourselves that it would be robust, and it did survive pretty well. The shoe itself is a carbon copper composite developed by a company which does supply shoes to the underground. Now, obviously, underground and other third rail systems and fourth rail systems normally use cast iron shoes. The problem with that, with the high currents we're talking about, is that you would essentially end up welding the shoes to the rails. So this composite is the correct combination of conductivity and insulation, if you like, to stop it doing that. It's nothing particularly novel. It's been around for a few years, the material, but it's the first application in this sort of thing. The trackside battery banks are fairly simple in principle. They're just a 20-foot shipping container, half of which is devoted to the storage batteries, and the other half is devoted to the electrical equipment. This has got its own HVAC unit, as you can see, to thermally manage the batteries in there. It's also got its own fire suppression system. It's got, all the Wi-Fi connections to it. It's got an emergency stop, all of that. So we're putting 2 of these down at West Ealing eventually. One is, each 20-foot container serves one of the 2. The train is 3 cars long, and the 2 outermost cars are the driving motor cars, which have the batteries on them. So there's 1 container per driving motor car. And these are supplied by a company called PowerStar in Sheffield. Just going back to the train, the train has 3 batteries per driving motor car. Because of history, this is there's a slight bodge, you might say, at the moment. Basically, you can only have 2 batteries at the moment connected to the traction control unit, and the 3rd battery is switched in and out. Can be automatically and can also be done manually. That's because the traction control unit we've got on this train is a little bit limited in the power it can handle, for historical reasons, because we wanted to get this train to COP26 and demonstrate to the public. So this is what we've got on the trial unit, is a bit suboptimal. What we would do in future is we'd have all 3 batteries connected in parallel with a different type of TCU, which can handle the high charging powers. That's a bit of a detail for the future. Now, just one thing that really has been a challenge has been the approvals for all of this. It's a joint project between, well, it was originally Vivarail as a supplier to Great Western, Great Western being the entity in charge of maintenance and the operator of the unit, obviously, and also Network Rail, because it's obviously trialing new infrastructure on their infrastructure. So we're all now, one project team, Great Western and Network Rail, reporting to the DFT. So it's a DFT sponsored project. But this is the approvals map that I eventually put together earlier this year, just trying to get my head around everything. It's a mixture of CSM, which is CSMRA regulations, compatibility, so obviously the mandatory train and infrastructure compatibility work you have to do, Great Western's own internal. I won't go into detail, but you can see the complication there. So this is what we're currently working through at this stage in the project. There's a lot of interrelationships between the various approval processes. So if you thought just getting a new fleet of trains introduced was complicated, try doing it with a new bit of infrastructure as well. We have, in recent times, had the benefit of a couple of graduates working for us. Started with a chap called Eric, who started with us in Vivarail days, and This year it's been a chap called Jonathan, and both are absolute whiz kids when it comes to programming and simulations, and they use a software tool called Python. And through their work, we've developed a simulation tool, principally to try and predict the performance of the train. I mean, in the early days, we did very basic performance calculations on the spreadsheet, but what we've got now is much more advanced. We've got a simulation tool which can be built up from the component level upwards, if you like. So it's got this architecture, very modular, where you can build up a train model, and then you can superimpose on that a diagram, as in a train working a diagram as a set of routes and a timetable, and then several diagrams come together to form a timetable on any given route, and you can load in the route attributes, you can vary the train parameters, all that. So in essence, you can, with this, what we now call the battery train network simulator, you can model not only one battery train on its own, but you can model a whole fleet of battery trains over many different routes. We've not done that yet. We've only done one train, but in principle, this tool can be expanded. This is a slightly more detailed level about how that component-driven architecture is built up. I can't even pretend to understand the coding behind it, but this is on the left there. That picture shows the sort of architecture you might start with, involving traction motors, inverters, 4QCs, transformers, pantograph. In principle, you can have all of that, and you just delete what's not appropriate. So our train, for example, doesn't have a pantograph and doesn't have a transformer, so you don't need all that. But a project that Vivarail was working on the 321 Renatus units, class 321 Renatus, was a lot more complicated and looked a lot more like that picture on the left there. And then, of course, you can have different ways of charging the battery. It might be through the charging rails over to the right of the diagram. It might be through a shore supply. And it could also be through the 25 kV through a transformer. So by building it up in that way, you can then model each of the elements in the system very accurately, as a sort of black box with parameters and inputs and outputs. And you can build up your model of your train. These are all the sort of things that you have to consider when you're simulating a train. Obviously, no surprise to most people, but there's a lot of variables when it comes to. I mean, the main point is you're trying to estimate how much energy the train is going to use for a given route, because obviously that's very important to the size of the batteries and also how long it needs to spend on charge. So you've got things like the mass of the train, number of cars, the resistance characteristic, which is known as the Davis equation, and number of motors. The auxiliary power loads are very significant normally in terms of what your range is for your battery train. You'd think it'd be things like the gradients on a route. Well, it is, but also it's equally what's equally as important is the hotel loads, really. So you can model all that, and then you can also do some optional things, like you can investigate what happens if certain things fail, like, for example, if the fast charging system is out of action for a couple of hours, or if you've got a very hot day or a very cold day. You can look at different types of driving style. There's basically this sort of unlimited things you can do with this simulation tool, and increasingly we've been getting more and more interest in this from other parties. So these are the specific parameters that we've been using in our model of 23001, the 3-car battery train for the Greenford trial. It's a 57-meter long train. It's got 6 84 kilowatt-hour batteries. That is I should say that battery capacity stated is what we call end-of-life capacity. We try and be conservative with our calculations without being too conservative. But we always generally work with the end-of-life battery capacity, which is always a little bit less than what it is when it's new, obviously. We've also assumed that we can only use a certain range of battery capacity as well. So we assume that we keep the batteries between 20 and 90% state of charge. You don't want to fill them up totally, because then you haven't got enough headroom for regen braking. Also, you don't want to discharge them too much, because that's bad for the batteries. but the batteries look after themselves essentially. That they won't, you can't drain them to 0%. The battery management system will stop that happening. The charging power is pretty impressive at the full rating of the system, which is basically 1,000 amps at 900 volts. That equates to 900 kilowatts per car. So we've got 2 cars that can charge, so that's 1.8 megawatts per train. Just to put that in perspective, 900 kilowatts per car, my house battery at home charges at 12 kilowatts, so that's 75 times more powerful than your average house battery. And other stuff here, age of the batteries, yes, talked about that. So we're talking about, we're doing all these simulations at end of life condition. You can model it with full crush loading, passenger loading, or you can model it fully seated. We've gone for something that's towards the busy end of the day, but not completely crush loaded all the time. That's one of the trade-offs you have to consider. You don't want to assume your train is fully crush loaded all the time. That's unrealistic. So we've gone for fully seated all day, plus some services being crush loaded. We've also gone for heaters on all the time, because like I say, the hotel loads can be very significant, and we've gone for a sort of aggressive driving style. And this is the sort of output you get from the tool. What you see there on the top is a typical graph showing the speed in green, speed profile, and distance in red. And then the state of charge is the blue line. So you can just see at the start of the graph, on the left-hand side of the graph, the state of charge of the batteries is going up. That I think is because what's it doing there? Well, you can see how the state of charge goes up and down depending on whether the train has stopped at the charging or not. It also recovers energy back into the battery, so you can see the blue line having a bit of an uptick when the train is braking. So you can see it models it quite accurately, but no model is complete without properly validating it against real life data. We had a bit of a chance to validate the model against 23001's real life energy consumption when we used it at COP26, but that was only 2 weeks worth of data. So one of the big benefits of the trial we're about to do is that we'll get a whole year's worth of data to validate the model against, specifically for a class 230 battery train. But of course, a lot of this is common to any type of battery train, as long as you know the mass and how many batteries, etc., and the architecture of the power system. So that's exciting to look forward to. We haven't done a huge amount of it yet, but we will get into that very soon when we start running the train day in, day out at on the Greenford branch. Coming towards sort of the last part of the presentation now. We've obviously since been taken over by Great Western. The main objective has been to get this trial up and running, and the trial will officially start when we've taken the train down to West Ealing and we've got the charge rails live. That will mark the actual start of the trial, and then it's a nominal 12-month trial through all seasons, and sort of all loading events, if you like. But obviously Great Western and the DfT are thinking beyond that about how might this be used on other lines. So we've already started looking at the technical and business case of rolling it out to other lines on Great Western. And this is just a bit of a process flow, if you like, to show that it's an iterative process, not just the technical simulations, but also the business and the operational case. But I'm mostly going to talk about the technical feasibility studies we've done so far using our simulation tool. Just some of the things in favour of doing this using the fast charge system. Obviously, it's expensive in one respect because you have to carry batteries on the train, and we all know really that the best way to power electric train is directly through the overhead wire or through the third rail. It makes the trains a lot simpler. You haven't got to carry the mass of the battery around. The trains should be more reliable ultimately, and all of that. But we also know that the government doesn't appear to be, at least not in England, doesn't seem to have much of a plan for electrifying the network anytime soon. Obviously, Scotland is very different. So whilst there's this reluctance to electrify, rightly or wrongly, You know, battery trains are one of the two, well, probably the front runner really for alternatives for self-powered trains where you want to get rid of diesel. And of course, they do have other advantages. With a battery train, as long as you charge it on the line it's going to operate, you don't need to then run it back to the depot to refuel, so you reduce your empty coaching stop mileage. They should be a lot cheaper to maintain than a diesel unit because of the lack of moving parts, although obviously there's a cost associated with the batteries in the first place. And obviously they have benefits for decarbonisation and also air quality, but you knew all that. So I'm just to round off the presentation, I'm just going to talk about the work we've been doing on some of the other Great Western branch lines, principally the Thames Valley branch lines, which is West Ealing to Greenford, Slough to Windsor, Maidenhead to Marlow via Bourne End, where it turns back, and Twyford to Henley. Obviously, Great Western does have other branch lines, particularly in Devon and Cornwall, but we focused on the Thames Valley because of because it's close to Reading. The 23001 will be based at West Ealing most of the time when it's operating up and down the Greenford branch, but it will go back to Reading for maintenance. But this means also that if we roll it out the other branch lines, then we can have a common fleet of 230s, and we think we need about 7 or 8 really to make this feasible. And they would rotate around the branch lines, but all essentially get maintained at Reading. They wouldn't need to all come back to Reading every night. They'd only come back when they need to for 28-day exam. But the work we've done so far identifies the best place to put these fast charge battery banks would be at Slough, Bourne End and Henley. Just to go a little bit more into detail of that, it's well, Slough is I think Slough is to do with the proximity to a good DNO connection. The DNO connection is essentially the grid connection. Bourne End is useful because sometimes there's only one train on that branch line going between Maidenhead and Marlow, turning back at Bourne End. But at other times, it's 2 trains, one shuttling between Marlow and Bourne End, and the other one going between Bourne End and Maidenhead. So we thought by putting 2 fast charge systems in at Bourne End, it could allow for both eventualities. And Henley on Thames is just is there because during the regatta, the Henley regatta, they quite often have to strengthen the trains to double the length, and you'd have to put charging station in 2 platforms Twyford on the main line, which is for various reasons is not so practical. So we've plumped for Henley. Then we've used our simulation tool to assess the energy consumption on each route. So I'm just going to step through each of these lines just to give a flavour for some of the figures. So the Henley branch charged at Henley is essentially a 30-kilometre round trip, uses about 15% of the installed battery capacity for that one round trip, and would only require 2 minutes 17 seconds at Henley to recharge. So that's all right. Marlow, it's even shorter, so only uses 12%. And what we're considering here is a standard fleet of trains. So you could say, yes, okay, some of the trains might have a bit too much battery on board for the routes in question, but you've also got to consider having a common fleet of trains that can serve all the branch lines. So you have to essentially size it for the heaviest duty one. So Marlow does that, uses about 12%, about 1 minute 50 to charge. The other part of that branch is slightly longer, uses maybe 23% in a round trip and takes about 3 minutes to charge. So these are all well within the existing turnaround times. Bourne End's got a particular constraint. It's got a set of points that's close to the end of the platform, but we've basically checked that the Class 230 would fit there, and it would, which is good. Windsor and Eton is, again, a very easy little branch line, hardly uses much energy at all. And we talked about Greenford, and that's where we're doing the trial. What you also have to consider is the energy required to get it back to the depot, which is a bit more challenging. So we've looked at that as well. Henley to Reading uses about 23% of the energy, of the capacity rather, the battery. When it gets to the depot, it wouldn't be charged on the fast charge system. It would be charged via a much lower power plug-in sort of short supply. So we have to allow for that, and we've calculated that it would take maybe 2 or 3 hours to charge in the depot. yes, just to go off on a bit of a tangent, when it comes to actually installing these fast charge systems, you really have to be conscious of the local grid supply. Now, in some respects, the system is friendly to the local supply, because you're only looking for a low power, low voltage, really a 3-phase connection, no different really to what you might have in your house, rather than looking for something that comes off the 32,000 volts or higher part of the network. But so to charge those trackside batteries, we've assumed you just need a 415 volt 3-phase 65 amp connection. So in some parts of the world, that's fairly easy. You get these maps when you talk to the local electricity supply company. They produce these maps to show you how constrained the grid is. So here you can see at Henley, all the local supply points are quite constrained, which means that to get a connection is going to take longer and cost more money probably. Whereas when you go to, we're back to the graphs here of how much energy it uses to get back to the depot. But here you can see at Bourne End, the local supply is a lot less constrained, which is good. So it's just something you have to be conscious of with this system. And of course, it'd be no different if you're electrifying, because you've got to get the power from somewhere. The Great Western Main Line does benefit from having a lot of extra electrical capacity. So you might say, well, why don't you just charge them at the mainline end, which is also a possibility, but then you have to step the voltage down with a transformer to charge the trackside batteries. As you move further away from Reading, obviously the train uses more energy to get there and back, so you're talking about longer depot charging times, but nothing that's really completely impractical. Slough has got loads of unconstrained loads of power, because they have a lot of industry, so there's no real problem at Slough. And West Ealing is the furthest away from Reading. But all through our feasibility work with the simulator tool, it's all perfectly feasible, we think. And now it's just a matter of convincing the DFT to make a decision and let us carry on. But what I've shown here is it could be equally applied to the West Country branch lines, Bristol, even other parts of the country as well, if this catches on, and which we hope it will. And that's it. Come to a bit of a abrupt end there, but I hope that gives you a pretty good flavour for what we've been up to and why we're doing it. And we hope that after this year there'll be plenty more life in it as well when we hopefully roll it out to other branch lines. So thank you very much.
David, that was fantastic. Thank you very, very much for that very in-depth presentation and the knowledge that you've clearly got on the subject there. So we have got a number of questions that have been raised. So let me just open the chat. I want it in a separate window if I can. Why won't it give me in a separate window? So anyway, so yes, if you have any further questions, please put them in the chat, or if you want to ask them in person, if you put the raised hand up, come to you in turn and in an orderly manner. There was a very early question. Let me scroll back up. This was from Stephen. Stephen, you're more than welcome to ask the question yourself, or I can read it out for you. Well, I guess the silence is I'm reading it out, so that's not a problem. So Stephen says the grid to rail energy efficiency is about 80% for electrification. Okay, and for battery it's 65. But for the Vivarail, or the Great Western Train as it is now, which charges a pre-charged battery, which you clearly explained, must be less, because you effectively charge the battery and then you're charging the battery again.
Yeah.
So yeah, how the crux of the question at the bottom is how much is better than hydrogen? Maybe as an unfair comparator, but anyway, I think you get the gist of the question.
Yes. Yeah, I think you're about right with the 65% I think it's about 60% overall if you think from grid to train, when you even including the charging of the trackside batteries. When I calculated it for a hydrogen train, and this was about 5 years ago, it came out at about 38% well to wheel efficiency. So it's still much better than hydrogen from an efficiency perspective.
Oh, okay, that's good. That's good. Right, so let's move on. Right, right, this is from Gareth. Gareth, who says, has any thought been given to developing a set of standards for the positioning in the forefoot to support interoperability of future fast charging trains?
Yes. Well, yeah. So in Vivarail days, we had hoped, as a company hoping to sell this technology, we had hoped this would become, the standard for fast charging in inverted commas. We did engage with the RSSB in the early days, but it didn't really come to anything. We've recently re-engaged with the RSSB, who are doing a project, I think it's T1172 or something, looking at battery charging systems. So we're now talking to them about that. It's a difficult one because it's not, you'd have to obviously make sure your trains are designed to allow for this system, which in practice means that you need to have a DC bus line along the train that can handle the charge currents.
We look at the illumination of the component itself. So what's been highlighted here is, or in this case,
Let's see if we can we mute everyone apart from David?
we also have interior lighting, which you'll see is on, but it doesn't really appear.
Sorry about this, David.
What's that question or not?
No, I think it's some background noise of a TV documentary or something. I'm not sure.
So yes, we are in the early stages of engaging with the RSSB. I think part of the problem is it's not, what we're doing is not terribly well known or understood. So there's a bit of an education piece going on to show what we're doing, and you can probably see from it. In one sense, it's the way that we've designed the shoe gear in particular could be applied to any type of train, but the trains have got to have the power architecture to allow for it. So you've got to have the TC, the traction control unit that can deal with it. You've got to have the space on the train to fit shoe gear. We, just as an aside, we designed the shoe gear so it wasn't bogie mounted, so that it wasn't bogie specific. So you could basically design it so it could bolt onto any underframe with a sort of interface bracket, with a view to making this standardized for other types of train. And I think that possibly slightly answers the next question as well about using existing third and fourth rail shoes.
Thank you, Dave. Appreciate it.
Yeah, the shoes, you couldn't, the original third and fourth rail shoes on the D78 stock, we could have used. In fact, in the very early days, we had a grant from Innovate UK, and just to demonstrate the concept, we did use the original third and fourth rail shoes. But I took the view that for the production version, if you like, we wanted to design the shoe gear so it was body mounted rather than bogie mounted. Again, as I say, just to make it so it's not tied to any particular bogie design, but also so it means it's in a less harsh vibration environment as well when it's.
And yes, you're above the primary suspension. Yeah.
So that's why we didn't use the original third and fourth rail shoes for charging.
Okay. And I think you mentioned in the presentation to sort of support Steve's question there that if you just use pure cast iron, you'd have a welding effect with the.
Yeah, that's right. Yeah, they weren't rated for that.
Being stationary for a period of time.
Yes.
That's right. Right. This next question's from Baker. I'm sorry, I've only got Baker. That's all you've got there. So I don't know who.
How much power is using the batteries? I don't know, to be honest, off the top of my head. It's probably only 5 or 10% or something like that. Okay. Not a huge amount.
Okay. Can I just ask a supplementary question to that? Does the high temperature of the batteries cause any early degradation of the batteries?
It would do if they were allowed to get to that sort of temperature. You could end up with, well, in the worst case, you'd end up with thermal runaway. But but you can also
yeah, and then we've got lithium-ion batteries, and which we all know there's big risks involved. Yeah, yeah,
yeah. So the thermal management system on the battery keeps it cool and also keeps it warm in the winter. That's the principle.
Okay.
So it keeps it within its comfortable operating range, and obviously doing that does use some power and obviously reduces your range. But without that, this wouldn't work. You have to manage that heat. That's fundamental to the whole safety of the system. Because there's several other factors that would have to come into play to get thermal runaway. There's loads of other stuff, design features that would hopefully guard against that. The mechanical design of the battery. It's a very
the segregation of cells and so on. Yeah,
yeah, and it's a very stable chemistry, lithium ion, or this particular version of lithium ion polymer.
okay.
As opposed to other types of lithium ion. So yes, that's that.
Okay. Right. So a question from Louise here. Do you want to ask this yourself, Louise, or do you want me to read it out? I'm easy.
Well, I've actually put several in, Andy. So
I know you have. I know you have. I was doing it in turn.
Things going.
I was not going to let you have the full reins all in one go.
No, I wouldn't attempt to run away with everything. So, so I was kind of pondering. One of the things that's easy to happen, David, is that people make tacit assumptions about, well, it's a train, isn't it? And in terms of operating, people assume with a diesel train that when you get perturbation, you can just leave it sitting there and it'll happily keep its passengers warm and in the light until you can get there to rescue it. But that's clearly not the case with a battery train, either a purely battery train or a battery EMU with intended to run on the overhead wires or the third rail as well. Yep. So I was pondering whether there's a kind of rule of thumb that we can start to provide the likes of control room people with, to say, well, the battery's this size, it's got N hours or N distance or N miles per hour, or say N miles, or that kind of thing, as a rule of thumb to help them understand that prioritization in managing perturbed situations or even planning, what their expectations and aspirations ought to be.
Yes, well, that is very much part of the trial. We've been thinking about that a lot, and it's going to have to come down to some sort of simple lookup table, I think, where you go, right, if you're stuck here, on the Greenford branch, it's little less of an issue because it's such a short branch line and it's charging every time it comes back to West Ealing. Given the size of the batteries on the train, you've got an awful lot of redundancy in reserve, so you can run the hotel loads probably on that line for a couple of hours without any and you can still get the train back to the depot for charging. But on other routes, yes, you'd have to be a lot more careful. The train will have a remote condition monitoring system, so there'll always be a back office monitoring the state of charge of the battery, and there'll be certain warnings that kick off at if the train's been stood for several. We can configure it how we want it to come up with some error messages or warnings that kick in, and then that can be fed back to the control room and then almost to the staff on the ground. But one of the debates we've always had is how much information do you give the driver? Because it's when you have an EV car, you have a range meter or whatever. It tells you how many miles the car thinks it's going to have left. The danger of giving too much information to drivers is that they'll interpret it in a negative fashion and just pull the train out of service. So our train only has this single light that says I'm charging or I'm not charging. Other than that, there's no information about the battery state of charge. That'll all be going back via the RCM system. But these operational rules are something we're going to have to figure out in the course of the next year and refine. In light of the operational experience we get. So yes, not a very clear-cut answer, I'm afraid, but certainly it's there in our.
It's okay. If it's the state of the art, David, that's all I can ask for.
Yeah.
Just to interrupt the flow of Louise's questions, if I could maybe ask one on hotel loans with modern passenger expectations of Wi-Fi and phone charging and laptop charging, if you are in a degraded state that you're going to be, are some of them facilities switched off, to conserve battery?
Yes, I mean obviously there's the mandatory loads that you have to keep supplied.
Lighting, heating,
lighting,
vents.
Ventilation. So that we have to, and we do comply with all that. We have to.
Yeah.
But for whatever it's 90 minutes, I think it is. But
But
yes,
Wi-Fi and phone charging is
Wi-Fi and phone charging. Yeah, but to be honest, the biggest loads are the heaters and all the air conditioning in the summer. The Wi-Fi is peanuts, really.
okay.
So I think we haven't got a very sophisticated load shedding system on the Class 230 because it's all very much relay based control. But other trains, newer rolling stock, you could be much more intelligent about load shedding. Linked to battery state of charge. So I've no doubt that other manufacturers are already thinking about that.
Yeah. And this technology is in its infancy, so these things can be thought about in future versions. Yeah. Right. So back to Louise then. Louise, do you want to ask your next question?
I have to remind myself what it was, Andy.
Okay, it's on the chat. What's the in the event of batteries approaching a minimum state of charge or charge level?
Ah, yes.
What plans are in place in the event of the batteries approaching them?
So yes, it's probably connected with the answer David
was, I guess, yes.
About developing the operational rules as we go.
Yes, I guess, I guess Stephen.
That's fine.
We calculated one of the perturbed scenarios we've modelled on the Greenford branch is what happens if the fast charge stations are down. If they lose.
Okay.
We could do about 9 round trips without any real problem, without charging.
Okay.
So that just gives you a flavour for the on that train. It can go quite a long way, basically. I mean, it can do 50 or 60 miles between charging. It doesn't have to on the Greenford branch. It charges every 8 miles because it can, because that's it's opportunity charging really. But it can, if push came to shove, do 50 or 60 miles before the batteries start getting low. So you'd be surprised.
So we have another question then from James France. So with peak daily temperatures ever increasing in the UK, doesn't feel how detrimental were the extreme environmental factors to the simulated performance?
That's another one I can't really answer. Although I said earlier that our simulator tool could do that, we haven't actually. I don't think we've actually simulated peak extreme temperatures. Probably ought to, but obviously one of the things about the trial is that it will be 12 months and through all seasons. So we'll find out in real life what happens. And I say,
hopefully we'll have a better summer next year.
Yeah, I mean, what will happen in practice is that the HVAC system on the battery will be working overtime to keep them cool within their optimal temperature range, which just means that it's going to drain the battery a bit faster. What that actually means in practice, I don't know. But on the Greenford line, you probably won't notice it because it's going to be visiting the charge station every half an hour.
Oh, yes. Right. So from Paul Saw, he wants to know what fuel economy is, kilowatt hours per mile. Is that the right units?
Yes, that's about right. Yeah. Hi, Paul. Yes. No,
I just thought it'd be good for people to know actually how incredibly economical a train is compared to cars, because like a big fat heavy SUV is about 2 kilowatt hours per mile, and I think when I was involved in the first trains, the whole train is like 1 kilowatt hour per mile. Is that right still?
Not quite. It's between 2.5 to 3 kilowatt hours per car per mile. So
okay, that's still good.
Between 6 and 9 kilowatt hours per train, per mile for the train. But it's still, as you say, it's still.
And what's that compared to some of the modern electric vehicles that we've got on the road now?
It shouldn't be too far off a normal EMU, really. It might be a bit less than the EMU.
A road automobile.
A road vehicle, yeah.
Oh, I don't know.
I think the best you'll get from an automobile car, maybe like a Tesla Model 3, is about 3-4 miles per kilowatt hour. But
miles per kilowatt would reverse the units, aren't we? Not kilowatts.
Sorry. So, but the big SUVs, where they're like approaching 3 tons.
Wow. Yeah.
It's nowhere near that.
Yeah. That is a massive economic, environmental benefit, then, isn't it? Yeah. Yeah. Well, right. So we're back to Louise. Louise. So back over to you, please. I think this is your last question I've seen on the chat.
I think you're probably right, Andy. So I was interested to understand whether you explored the sort of limits of applicability with a combination of motor cars or battery cars, fast charge points, and sort of range and speed to understand whether a sort of 3-car unit is about the limits of sensible application, or 5, 7, 9, 12, whatever it might be, and whatever drives that.
Yes. Yeah, I mean, it depends how many batteries you can fit on your train. So, you know, you can have a 5-car or 6-car train, and you can have maybe 3 of those cars got batteries on them, or maybe all the cars have got batteries. Obviously, the more cars carrying batteries that you have, the more complicated the charging arrangements become at your terminus stations or even our intermediate stations, because what we've tried to do with the 230 is keep the shoe gear quite close to the batteries that they charge to minimize the cable runs and the energy lost with it. So we were looking, for example, at a 4-car class 321 Eversholt unit, and that, when we were doing the feasibility for that, we were looking at 3 sets of shoe gear and 6 batteries spread all over the train, and that was very complicated. But that means that for every train or every charging location, you'd have to have 3 sets of charge rails. So it does get quite complicated the longer your train, which is why I think the fast charge system is the limit of applicability probably is going to be self-contained branch lines where you've only got sort of 1 or maybe 2 types of rolling stock. Obviously, as soon as you get more than 1 train wanting to use the fast charge system, you have to think carefully about where you position the rails. And
yeah,
and so there is a bit of a practical issue there. There's no reason why, if you had a long distance rural route with essentially 1 type of train on it, there's no reason why you couldn't deploy fast charge systems at intermediate locations. You'd have to make sure your trackside battery is sized for the frequency of traffic using it, because obviously you don't want the batteries on the trackside charger running out too quickly, and also then be conscious of the, you know, how close, what size grid connection you can get as well. So it's one of these where you need to think about the entire system, and that does, you know, bring complications with it. And ultimately, you know, I think our main competitor here is going to be battery trains that charge from the overhead wire, because the overhead wire can be as long as you want it to be. It can serve any train with a pantograph, and although there are limits to how much current you can put through the pantograph and wire interface, you've got a much higher voltage, obviously.
Yeah.
So, but what you can't necessarily do is link that to a battery storage element as well, for rural. So, you know, at the moment we're doing a bit of work. We've kind of sort of stood back and go, right, what's the real advantage of this technology? Because back in Vivarail days, it was, you know, we were trying to sell something, but now we're part of the national rail system, if you like. It's that'll be successful, and I've no doubt it can be applied to other branch lines. But as to its wider applicability, it'd be nice to see it on some longer runs with intermediate stations rather than terminus stations. And it'd be nice to see it fitted to other types of rolling stock as well, as another tool in the box sort of thing. That's to be seen.
So, Mr. Baker's asking the projected battery life.
Yes, we work at the moment. We work on the basis of about 8 to 10 years. That doesn't mean you chuck the entire battery at the end of it. Battery recycling now is really coming up. And obviously all the EV manufacturers are studying this very hard, and a lot of universities. So I think recyclability of these batteries will only improve to the point where you may be able to recycle 90–95% of it. And for us, with this system, one of the nice things is, in theory, you can take the batteries that are on the train and put them in the trackside battery bank, where they'll have a more gentle life. And then even after that, you can then, you know, put them into sort of home storage applications. And even after that, you then recycle them. So it might even have 3 or 4 lives before they have to be recycled. Which, if you can get the value of that, means that you're not talking about buying a new battery every 10 years. So that's actually that sort of system has got to be set up. It's all very well saying in principle it's a good idea, but actually getting it to work in practice.
Well, the quantity of lithium worldwide is going to be a question, isn't it? For
Exactly. Yeah. And there'll always be a demand for second-hand batteries. So it probably won't cost. The cost is only going to come down.
Yes. Yeah. Right. So Peter Woodbridge is on about would all moves to from Reading be empty coaching stock? I think currently the first and last service to Henley, for example, do operate as passenger services.
Right. Yes. Yeah. With the Greenford trial, the moves to and from Reading approximately once a month will be ECS. The limitation with the Class 230, it's got a 60-mile-an-hour top speed, unfortunately. So that means it's going to have to go on the relief lines to Reading, which is problematic from a paving perspective. But one of the things it might have to do is go in and out of Paddington on the last train of the day, believe it or not, because I think when you sweep the train for sleeping people and drunk people at the end of the day, the staff for that are based at Paddington. So we're doing the compatibility work to run the battery train into Paddington, the last train of the day. So that'll be interesting. But it can do whatever it needs to do.
No. Okay. Right. So Lawrence, I think we've answered that. It's lithium ion, isn't it? Lithium ion polymer.
Lithium ion polymer, yes.
Oh, so yeah. Okay. So that's that. Right. From Stuart DeBoer, presumably for longer routes, you could have intermediate charging points at intermediate stations.
Yes, that's right. Yes, you could do.
So I demonstrated that with your diagrams, yeah. Right, Robert Pritchard, fascinating presentation. When can we expect to ride on the train on the Greenford branch?
Yes, next spring, hopefully. There's a lot of approvals to do between now and then. The train is physically currently at Longmarston Innovation Centre, which is owned by Porterbrook in the Midlands, near Stratford-upon-Avon. What else to say on that? It will be used on a 6-day-a-week service. There will be a Class 165 on standby, essentially, in case we need to withdraw the train for any reason. And that's another reason why we're doing on that branch line, is that anything that goes wrong or needs fixing won't have a huge impact on the customers. But yes, 6-day-a-week.
Okay. Right. Laurie has asked, is the BTNS, I'm not sure what that stands for, open source?
The simulation tool, yeah.
Okay,
no, no, it's owned by Great Western now, really. It's a good question about the intellectual property and stuff, because Great Western is now, essentially on contract to DFT. And the DFT don't quite know what to do with the intellectual property they've purchased from the receivers of Vivarail. But it would be nice if we could find a way that we could use the BTNS for other operators to have a look at. So we've had quite a bit of interest in that. And Jonathan is the only person who knows how to use it at the moment. And he's gone back to university. So
it's all written in Python scripted.
Yeah, he's going to write a manual so that I can have a go using it. But
right. Right, I've got the same question from Steve again. Is that a different question, Steve, or I think it's a repeat, is it, of your previous question? No, I think it is. It doesn't seem to be. So the composite shoes were used for first trial Innovate UK, but the standard shoe beam was used. I don't understand. That's not a question, is it? As such, that's just a statement, is it?
That was me just answering that question.
Yeah. Right. Okay, yeah. Thank you, Paul. Okay, so that's helped to answer Steve's question. Right. So we've got. Please pardon me if it's a silly question. Was the floor of the whole vehicle charged, or just the section above the batteries?
Just the section above the batteries, really, or only where we needed to run the extra cables. Yeah. So basically cut a rectangle in the floor and laid this new floor down to carry the cables.
Okay.
Just something that
Right, we're nearly there. We're nearly there, David. You can go and have your.
that's all right.
So, Rob Whitby has raised a good question. Is there scope for incorporate solar panels on the train roof to extend the battery life in future?
Yes, but they don't really offer much of a. You don't get much power out of them. So
No.
obviously, there's the gauging issue. There's what do you do about tunnel. So I don't think it's practical to put on the train roof. But you could.
I was thinking on the charging station.
Yeah,
so
that would be better probably. So you certainly get some benefit from having them on the a roof of the charge container or near the charge container.
Yeah.
Oh,
wow.
Or in the station roof. That's another possibility.
Yeah.
Build a new station.
How to make the battery raft mass distribution friendly. So,
right. Well, the best way to do that is to start with a new train and design the battery or specify the battery how you want it. With the Class 230, we ended up with the battery looking like a genset and had to kind of live with it like that for various, timescale reasons. But if you were designing it from scratch, you could do a lot with you could probably distribute the mass like they do on a Tesla. You actually sort of build the battery into the floor of the car, and if you design the train like that from the beginning, you could be much more intelligent about how you distribute the mass of the battery, and you can also incorporate heat recovery as well for your cooling systems on the train. So there's a huge amount of opportunity with how you design a battery train if you start from scratch. When you're retrofitting batteries to a train, you're much more constrained.
Confined, yeah. Oh, right. The last question then was a direct battery train charger, with track power converters, and not a trackside battery bank ever explored?
I don't know actually. Paul might be able to answer that question because he was involved with the original Innovate UK work, but I don't think it was. But if you could do.
Coming back on.
Sorry, I'll say it again.
So yeah, it says was a direct battery charger, a trackside power converter, not a trackside battery ever explored.
Could you do it
without? The problem was you would need a big supermarket has a 33 kilowatt power supply. That is not enough for automotive cars, let alone a train. And if you need to replace a load of electricity in 10 minutes, a big chunk of the battery, you're going to need about a megawatt, and you're not going to get that from the grid unless it's an overhead line. And as Dave said before, you've got to be close. So you're finding this at service stations. They need to put a battery, which is basically an enormous capacitor, top it up when it's quiet, so you can do 200-300 kilowatt hour supplies to fast charge your car, let alone your train. So the problem is you haven't got the connection. It's quite rare.
Fully understand that. Yeah. Right. Well, that brings us to the end of the questions. You've done remarkably well there, answering and supplying all the answers there, David. So I'm going to quickly hand you over to Sam, who's going to give us a vote of thanks.
David, thank you for that interesting and entertaining technical talk. The Greenford line, and I'll say it here, has got a personal interest to me. I grew up in Greenford, so I have traveled on that branch line many times. And seeing a district line train on the Greenford line, I think it's going to blow my mind when I see it, but I am looking forward to seeing that. What was really interesting from your talk, it was great to see that you're using FEA and real world testing and validating those computer models, and it's fantastic to see computer models being used to demonstrate engineering. The versatility and the traction, the fact that you can put a diesel engine on it, or a battery supply, or third rail is fantastic to see that you've got that modular ability to adapt the train to the needs of the environment it's going into. I really did like the battery simulator. I think that's, again, computer modeling to demonstrate and test out your models beforehand. That was really interesting to see, and the use of Python as well, and to see that being brought into the mainstream and moving away from Excel, as you were saying, using and looking at more powerful computer modeling, which was good. But you also highlighted the challenges of battery trains, and it's not just putting a battery on it, it's being able to charge it, and it's not just putting a feeder station into it. You've actually got to then connect it to the national grid, which in itself is a huge challenge, because our grid isn't necessarily always designed, especially on branch lines. You don't always have that huge amount of power available to use. So I was interested to show that you've also seen those challenges. So overall, I'm really excited to be able to, looking forward to seeing this train actually in use. And the other thing I did like about it was the Greenford line was always the first to be cancelled. The amount of times I've been stuck at Paddington or any Broadway and it's been cancelled. Now we're going to have a battery train with a backup train. Exactly. So you've been able to do it and give the Greenford line its well needed extra train. But I'd like everyone to join in a round of applause or raising your hands and to say thank you, David, for such a fantastic talk. So thank you.
Yes, thank you.
Yeah.
So yes, so thank you very much. If I can just remind people, our next event, 9th of November in York. It's the National Chairman, Andrew Skinner. So please come along. It's going to be at the Priory Street Centre, which many of you will be familiar with. We've been there a couple of times now. Have an enjoyable rest of the evening, and once again, thank you to David. Oh, that's really fantastic. Oh,
yeah,
so
thanks again.
Thank you very much.
Good night, everyone. Good night.
Cheers.
Right. Thank you, Sam.
So was that all right?
Yeah, that was brilliant. Yeah, nice roundup and good thanks there. Yes, thank you. Oh. Right, I'll see members of the committee on Monday evening for a debrief, and that will do. So thank you very much. That's all right.